Good morning. I would like to make a presentation. Conversion of bioelectric sEMG signals into analog form for the BLDC motor's control. To begin with, I would like to present briefly the plan of presentation. Introduction, the EMG signal processing system, measurement and execution system, the measurement method, conclusions. EMG signals are widely used in today's technology. They are successfully used to diagnose and treat some neurological disorders. Considering the low voltage range, very high requirements are placed on the measuring apparatus to determine the sEMG signal level as accurately as possible. Advanced measurement probes with implemented preamplifiers that amplify the signal already at the muscle are available on the market. In addition, probes with built-in wireless communication modules can also be found so that the user's movements are not restrained. This has also contributed to the development of advanced prostheses, which greatly facilitate the lives of amputees. Over time, they gain new capabilities and are increasingly integrated with the operator, the person without a limb. Methods described in the literature on surface electromyography were used to build a system for collecting measurement data from the skin surface. A general schematic of the implementation of the measurement system is shown in the picture. The operation of the system begins with the collection of voltage data from the skin surface to read the sEMG signals generated by the motor units present in the muscles. The collected signal has a low amplitude, about 2 MV, so a high gain was initially applied to separate the important data from noise. In the next stages, it was cleaned of unwanted frequencies using a high-pass filter, straightened in a full-wave rectifier, smoothed with a low-pass filter, and converted to a digital value, where, in a further stage, this value will be processed by a computing unit, and then encoded with a compressed message and sent via Bluetooth interface to the control system. The measurement of sEMG signals begins with the collection of bioelectric signals from the skin surface at the site of the active muscle. For this purpose, suction cup angle measurement probes were used. To improve contact and reduce the influence of skin impedance at the contact sites, the skin was degreased and a gel was applied to increase the conductivity and adhesion of the probes used. The first step in analog signal processing is the high gain of the collected data. Its purpose is to extract the signal being examined from the background noise. An instrumental amplifier model AD620ARZ was used as the amplification circuit. It is characterized by a broad gain capability, up to 10,000 times, a small input unbalanced voltage, 50, and a low drift, 0.6 degrees Celsius. Assuming an initial differential signal gain of G equals 500, and using the closest resistor in the series, 100 Ω, a gain of 495 was obtained. To verify the system's operation, a test was carried out using a measuring station equipped with a measuring card and having symmetrical analog inputs with a measurement range of plus or minus 10 V. The signals from the biceps muscle were recorded at a sampling frequency of 10 kHz. The recorded signal of a single contraction is shown in the picture. Analyzing the data, it can be seen that the amplitude of the signal is about 2 V, which, when divided by the generated gain, 495, gives a range of change in the source signal of 4 MV, which is within the range of a standard signal. The next step in the test is to check the frequency of the examined signal. Using the fast Fourier transform, the effects are shown in the graph. It can be seen that most of the signal bandwidth is in the range up to about 500 Hz, which agrees with literature data. The next stage belonging to the preamplification is the use of an inverting amplifier with a gain of 2. For this task, a quadruple amplifier LM324 was used. With this solution, we have 4 operational amplifiers that will be used for the next steps of signal processing in a single chip. In this case, one of them was used in the inverting amplifier configuration, giving the output of the instrumental amplifier to the input of the inverting amplifier. A signal with a total gain of G equals minus 990 was obtained. The next step is high-pass filtering. Its purpose is to process the input analog signal in such a way as to isolate the low-frequency signal. This will allow further processing of the signal cleared of amplitudes with frequencies lower than the filter's design limiting frequency and cancel the DC offset occurring in the previous stage. In the present design, a first-order active filter without gain was chosen. For this purpose, another of the LM324 amplifier subcircuits used during preamplification was used. A passband cutoff frequency of approximately 100 Hz was assumed. It was decided to use a 10 NF capacitor, which was the basis for determining the resistor value, which was
150 kW.
The determined filter can be presented in the form of the following operator transmittance. Using it, the phase frequency characteristic of the design filter was made. After processing the signal with a high-pass filter, the negative amplitude must be removed because the microcontroller used later does not have symmetrical inputs, only analog inputs with an acceptable range of 0.5 volts. Removing this amplitude alone would generate data with very high dynamics of change, which would make digital processing much more difficult. The solution to this obstacle is to reflect the negative amplitudes relative to the equilibrium position and then smooth them. Such an operation will allow obtaining a signal with significantly reduced dynamics and, simultaneously, locally stable and allowing its unambiguous interpretation by a microcontroller. For this purpose, a precise full-wave rectifier was used, whose construction was based on two operational amplifiers. The created circuit was tested, and the signal was processed with it after high-pass filter treatment, which gave the following results. The next step is to prepare the signal for free reading by the microcontroller. The purpose of low-pass filtering is to limit the rate of change of the signal to such an extent that the signal changes its characteristics from AC to DC. Its steep slopes will be smoothed, thus changing the signal's frequency. The first-order active low-pass filter is used, whose construction is based on an operational amplifier and passive elements in the form of resistors and a capacitor. The limiting frequency was assumed to be 2 Hz, which should sufficiently smooth the processed signal of high-frequency EMG. A test was performed using such a design filter to check its filtering capabilities. The signal processed by a precision full-wave rectifier was used as the signal source. The resulting signal is significantly smoothed, but it is inverted and has too low an amplitude to be processed freely by the microcontroller. A final inverting amplifier with an adjustable gain was made to improve its properties. Using this circuit makes it possible to adjust the amplitude of the output signal to the individual physical conditions of the user. This circuit was made similarly to others in the previous sections on the LM324 operational amplifier. The wiring diagram of the circuit is shown in picture. As a result, an amplified and inverted signal prepared for digital processing was obtained. This work presents the design of an analog processing circuit for collected data. The performance of this task began with designing a pre-gain module using commercially available instrumental and operational amplifier. The high-pass filter, full-wave rectifier, low-pass filter, and calibration gain circuit were designed similarly. At each stage, the characteristic parameters of the circuits were determined, and the waveforms of the shaped signals were presented, thus giving a complete insight into the performance of the analog processing module. The data acquisition system correctly receives and processes the sEMG signals. The resulting signal is prepared for processing by digital systems. The frequency of the input signals agrees with the parameters from the literature. The completed project will serve as a basis to start work on a device controlled by EMG signals, in the form of a BLDC drive powering a prosthetic hand. Thank you for your attention.